All right, we'd like to go ahead and get started. Want to thank everybody for attending today. Today's topic will be confirming the accuracy of open channel flow and primarily flow data. My name is Rick Dye. I'm the Business Development Manager for Flowmeter Products from Teledyne ISCO. Accompanying me is Steve McManus, who is a Senior Products Support Specialist, and we're both on the Teledyne ISCO Water Platform team, if you will. You probably have talked to one or both of us in your years working with us, and hopefully we've been able to help you a lot. But Steve has a wealth of knowledge. Today what we're going to do is we're going to go through some of the standard open channel techniques, and we're going to talk about area velocity. We're going to go through the the latest technologies. So for that, I'm going to go ahead and turn it over to Steve.
Thank you, Rick. I too would like to thank everybody for attending today, and we thank you for taking the time out of your day to spend a little bit of time with us here in discussing this topic. First of all, just want to talk about why do we want to measure flow. There are a variety of activities that one would want to monitor flow from. First of all, I&I studies is one such example where a municipality or collection system would want to target and identify where there's need for some rehabilitation or work on leaky sewer pipes. There could be needs to monitor for enforcement requirements where an industry or a given location is required to monitor their flow and report to the municipality on what is the amount of flow being discharged. This could be for billing activities. If a village or a small community is passing their treatment on to a larger entity and they are being billed based upon the amount of flow that they are passing to that secondary entity, they would be billed based upon the number of gallons that are being recorded at that transfer location. There are several examples of cities throughout the U.S. that take part in such of a transfer process. Atlanta, Phoenix, Milwaukee, Boston, Denver are all examples of this type of monitoring. Wanted to talk about, at least show briefly here, the flow bench that we have in our lab. That we are able to test our equipment under a variety of pipe sizes, flow conditions, different velocities, different slopes, different hydraulic conditions, and this enables us to be able to test and improve our equipment under a wide variety of flow hydraulic conditions. In a normal open channel flow, oftentimes there will be primary devices installed. This would be a wide variety of flumes and weirs, which are generally, if properly installed under free flow conditions, expected to have accuracies in the plus or minus 5% range. Primary devices have been commonly used in the industry for a number of years. Matter of fact, weirs were used way back in the Roman Empire under the aqueduct system. When you're dealing with a primary device, there's only one measurement required, and it's important to note that we are not actually measuring flow. Flow is a derivative of another measurement or measurements, and in the case of a primary device, that measurement is level. We are measuring the level via ultrasonic technology, pressure transducer, or a bubbler system, and that measured level is then put into a calculation to derive the flow rate based upon that measured level and the configured primary device in place. It is very easy to verify that the meter is measuring proper level as one is able to use a ruler to take a physical measurement and compare that with the displayed level on the monitoring device. The ISCO Open Channel Flow Measurement Handbook is a great resource. It is often referred to as the Flow Bible. It has a wealth of information related to a variety of primary devices, different flows, and different primary devices, And then the latter half of the book is a myriad of level to flow data tables that one is able to utilize to validate the level and flow information that is being displayed on their meter. When a flume is accurately installed, meaning it is level on all axes, as well as there is no obstructions or things within the channel that can obstruct the flow, you will get that 3 to 5% accuracy. The chart we have in front of us right now is a 8-inch Palmer bolus flume collected from a signature with a 310 ultrasonic sensor. In the case of a Palmer bolus flume, the zero level is not the floor of the channel. So it is possible that one could have negative levels logged if there is a draining effect that will cause the water to go below the 0 point through that flume. However, as you see here in this data as indicated by the level going below the dashed line, which is 0, we are going below 0 here. This could be an indication of a miscalibration. Therefore, it would behoove one to go out and check to validate that indeed we have proper level calibration in this particular location. However, in the vein of validating the performance of the unit here, one should also note that the third pane here, which is an indication of the ultrasonic signal strength, is indicating that we have a consistently good 92 to 95% signal strength with the ultrasonic sensor here. So what that does tell us is that this particular sensor is reading very well in the primary device here. There are no concerns based upon the indication of how it's measuring level here. For equipment options, there are both AC and DC power options available. Typically, the AC will be for permanent sites where the unit is staying in the same location, and that would be often a signature meter. But a signature meter can also be used in a portable application. It does have the ability to be powered by a battery. Other options for portable equipment would be the 2100 series flow modules. And as shown here, we see a 2160 flow module that would be utilized predominantly with the LaserFlow sensor. The signature meter has a wide variety of flexibility and capabilities as displayed by this image. I won't go into every possibility here, but as you can see, we have a variety of communication methods. We have a variety of interfaces for different sensor devices and parameter monitoring, as well as a sampler interface. If you have need for these particular parameters and features, the signature meter would be the meter of selection here. For area velocity flow measurement, unlike a flume, we now have a secondary parameter that comes in the mix, and that is velocity. In this particular continuity equation, which is what Q equals A times V is referred to as, Q is the flow rate, A is the area, which is derived from the level measurement and the channel shape and size that is programmed into the meter. Level measurement can be made via pressure sensor or an ultrasonic meter. And then velocity, which is V, is measured by the Doppler effect, which is the shift in frequency of the reflected energy from the sensor that is providing that measurement. It can be contact if you have a submerged pressure sensor, or non-contact in the example of the laser sensor. For accuracy verification, You certainly can measure the level and validate with a physical measurement via the ruler. And for the velocity data, you can use a secondary manual profile velocity meter device, but you can also utilize the quality statistics that are provided by the measurement device to validate the quality of performance. This is a side view of a submerged AV sensor that's in the pipe. It measures the level by pressure. Then, based upon the user-defined channel shape and size, it calculates the area represented by that flowing water. Then it measures the Doppler effect for velocity, and then it takes that calculated area times that measured velocity to derive the flow rate. This is an example of some data collected from a submerged area velocity sensor. The top pane is the level. The secondary pane there is velocity. There are a couple of things that jump out in this data that should cause one to ask some questions about this data. First of all, in the level data, you can see there are several sudden shifts in the appearance of the data, where it drops or rises within a matter of one or two measurements. This could be an indication of some debris building up in the pipe that is causing the level to build up and then breaking free, which is causing the level to drop. Couple that with the appearance of the velocity data here, where in Flowlink, the analysis software, it has been set to 0 any errors in velocity, and we can see that there are a number of errors in this particular data. This would be an indication that this site needs to have some inspection to try to identify what may be causing the measurement phenomena we see here in this data. We could have some silt, some sediment, or other debris built up that is impeding the measurement of velocity as well as impacting the level in this particular site. For sensor maintenance, obviously, again, just to reiterate, we have level calibration, which in the case of the laser sensor would be an ultrasonic method. Typically, ultrasonic sensors cannot drift by the very nature. However, there is possibility that the mounting bracket could have shifted its position because of someone bumping it, or it wasn't fully secured in place. So it is a good idea to do periodic calibration checks of an ultrasonic meter. Pressure transducers will have a reference line, and they breathe through a desiccant cartridge. So it is a good idea to periodically check and make sure that that desiccant is not saturated and putting the sensor at risk. Saturated desiccant could cause level errors. Best case scenario, worst case scenario, it could lead to sensor problems. Velocity verification, again, could be verified by a third-party profiler. Calibration is not required, but more importantly, taking a look at the advanced diagnostics that are available for those various velocity measurements will build your confidence in the quality of that velocity measurement. For the submerged probe, velocity as shown here on the right, they would be the signal strength, which in brief is an indication of the volume of the return signal. The spectrum strength, which is an indication of the information coming back that was left or retained after the algorithm went through to discern what was and what was not related to velocity. And the spectrum ratio, which is an indication of the amplitude or the weight of information that's indicating whatever direction of velocity is being reported. And a perfect application, you would expect that spectrum ratio to be at or near 100% the majority of time, regardless of whether it's reporting reverse or forward velocities. If that number is beginning to diminish, it could be an indication of hydraulic disruption due to debris, silt, sediment, sensor location in the pipe. Something may need to be adjusted for the location of that sensor in that particular scenario. The laser Doppler power is an indication of the quality or the strength of the signal coming back on a laser, and Rick will cover that in greater detail during his portion of the presentation. This is an indication of data from a LaserFlow sensor. In the top pane, we have two direct measurement pieces of information from the meter. That is the 360 level and the 360 distance. And then we have a third variable of level that's a derivative within the software, in this case Flowlink, of those two pieces of information. And this is a process that one can utilize to discern and evaluate the quality of level measurement. If you take the level and the distance values and add them together, in a perfect world, you should get a uniform, consistent number. If level goes up 1 inch, distance should go down 1 inch. If level goes down 1 inch, distance should go up 1 inch. And so therefore, the sum of those two variables should always equal the same amount. We see a little bit of noise here in the D value, the purple at the top there. That's indicating to us that there is a measure of difficulty or noise in the level measurement. If we drop to the third pane and look at the ultrasonic signal, we can see that our ultrasonic signal strength is dropping from the 80% region down to 20% and even below at times. That's an indication that something is causing some greater difficulty in the measurement of level here. Could be foam, could be turbulence. Something is inhibiting or decreasing, diminishing the quality of the level measurement here. However, having said that, if we again look at the level data, overall, it's looking really good here. So even despite the problems in having measurements, we are still getting good data out of this device. However, it would be advisable to have someone go out and inspect this flow, especially under the higher flow levels, where we see that that is when it's having the greatest problems or the diminished signal. And specifically, it's the transition from low to high flow levels that we're seeing this, or excuse me, it's when it's at the tail end of the high level and getting ready to drop that we're seeing this diminished signal strength. So it could be a hydraulic condition that just exists in this pipe, and if we're aware of it, good. The other thing to note is when that transition is when the velocity itself is dropping from the higher velocities, the 4 to 5 feet per second, down to around 2 feet per second, that we're seeing that greatest degree of measurement problems with the level. Again, this could be just a normal standard hydraulic position or condition in this pipe. Again, let's determine what's going on so that we can have the confidence in this data. This is another example of some data where the customer was viewing this data in a far more expanded span of data, so that little event that we see there just left or right of center was being seen or viewed as a spike in the data. There are many ways to view data for quality. There is no one answer. So as we began to zoom in on that data, we saw that there was some velocity dropouts beginning to occur prior to the event that we see in the middle. And as we see in this zoomed in result here, this is not a spike, but rather data that is over several hours where we're seeing the level rise from down at the lower values up to over 100 inches. and then it falls again over several hours, and then it rises again. And corresponding with that, we see impact in the velocity measurement that coincides. Level and velocity are two independent measurements. Therefore, this is telling us this was a real event. This is not equipment malfunction. Something happened in that pipe. Ultimately, what we found out is that there was a downstream lift station that failed and backed up the flow. The high level alarm was hit. The high level pump kicked on, pumped it down. Again, the pump shut off when it pumped it down, level built back up, high level kicked back on, and that repeated until it was understood that there was a problem at that lift station and it was corrected. This is real data, even though the data was somewhat abnormal. I will turn over to Rick Dye to talk in more detail about the LaserFlow.
Well, thanks, Steve, and great analysis, great detail on that. Again, if you guys have questions out there, feel free to get a hold of Steve. Steve is a wealth of knowledge and has been doing this for quite a long time. So we've learned a lot, all of us, including the learning area velocity technology, open channel flow, and the whole bit. So thank you, Steve. Let's go through principles of operation of what the laser does. So in the laser sensor, we have an ultrasonic sensor that's mounted in the back of the sensor. What it does, first thing it does, it transmits a beam to know where the water is. Once it knows where the water is, it focuses the laser below the surface of the water. So that's the patent, that's the magic behind the laser, is how it actually gets that velocity reading, and again, based on where that distance to the water is. Couple things that we do that's kind of unique with the laser. There's some advanced ultrasonic sensor diagnostics that are available. One is we look at the gain. So you'll see in the top left-hand side where the circle is, our gain is 65. What that means is we're not even breathing hard to get a reading. So it's getting a good, strong signal back, no problem. The one that would concern me a little bit more would be the quality, which is 40%. Or 40, and that should be normally closer to 90. So that means it's struggling a little bit to obtain that level reading. So that's something that we look at. Anytime you install one, you want to see that. Below is the graphic of what we're actually seeing. And it sees the peaks, and we're looking for the one at about 40 inches. So it sees there's multiple peaks there. So it's probably turbulent. All right, so let's talk about the velocity reading and what we do. We are transmitting a known frequency. We know the frequency we send out, what comes back. The Doppler shift, like a police radar gun, will tell you the speed of the water. So we know the distance, we know where the water is, we know where we want to focus to get the readings back. Another kind of visual here, a little front view, side view. There's the laser, it knows where the water is, and if you stuck your hand under a laser, you're gonna see a dot about the size of a coin, quarter, and what we're looking for is really the focal point, and that is known as the point of convergence. We take 5,000 velocity readings or scans, and we do that all in 2 seconds. So it does a lot in a very short amount of time to get that velocity reading back. Some of the diagnostics available on the laser, one would be the Doppler shift. So if you look at this scale on the bottom, that is frequency and speed, and that is the higher the velocity, it will be higher frequency. So in this case, we are getting a lot of reflections that agree with each other, which is what you want to see. You want to have, the more that agree, the better this signal is going to look. Typically, anything over about 500 is going to be a good reading. So in this case, we are 1,500 or 1,800. We are well above that. It likes what it sees. You will see another thing above that, X angle, Y angle, which tells you the pitch and roll of that sensor. And it has no problems. It likes that. X is 0 plus or minus 3. Y would be 45 plus or minus 3. And so we're right in range. Where this is particularly important is if your sensor were to ever go underwater and the water level drops back down. Do I need to go in and clean this? Do I need to do any maintenance? And in this particular case, we would say no. We have a good signal back, plenty of stuff in there to read, and our XY look good. So nothing is shifted on the mount. One thing that's unique about the laser is the signal to noise ratio. So the signal to noise ratio on a laser is incredible. Really what that is an indicator of the quality of the velocity reading. It's also stored in memory as a number called Doppler Power. Anything above 1,000 Doppler Power is considered good. In this case, if my velocity slows down, that peak will shift to the left. What's unique about the laser is that it can read really, really clean and really, really slow water because of the extreme signal to noise ratio that it has. So here's a good example of one. We're storing what we call Doppler Power. That is on the third pane. So you'll notice the level in the top pane was going along about 45 inches and then all of a sudden went way up. The velocity also in the pane 2 shot up, and the Doppler power eventually went out. So we have a high level, we had high velocity initially, and then everything went bad. So somebody needs to go there and do something, but this tells me that something happened at the site. It's not the meter. Okay, talk about some of the applications. High velocity, low level, steep slope pipes, low level raw wastewater applications. And typically anything less than 1 inch is almost unmeasurable unless you have a laser. So a normal area velocity sensor needs 1 inch before it even tries to read. Slow velocity applications, anything less than about a half foot per second is challenging at best. You'll see those in residential collection systems at times where they're looking for private property or personal property I&I. Slow clean applications, wastewater effluent, which is going to be hopefully clean if they do it right. Chlorine contact channels or UV disinfection channels. Drinking water influent is also challenging. Stormwater, you're going to see a lot of clean water there, but you're also going to see a wide fluctuation in the flow conditions. I go from very little flow to 10 feet deep. Irregular channel shapes, so we see that all as well. And there are ways to do level to area data points. Okay, let's look at a couple pictures here. Here's one that is a low level high velocity site, and this water is about a ½ inch deep and it's flowing about 9 feet per second. So really, really a challenging application. They were able to put a laser in and measure this. What we need though is a ½ inch, what we spec is a ½ inch minimum depth for velocity. We can read up to 15 feet per second. Low velocity, a lot more of these applications out there, and typically, again, anything below a ½ foot per second. Why is this difficult? Most sensors cannot handle the difference between the signal and the noise. They're so close to the same, they can't pick it out. The laser is unique to that. Why? Because it's got a very high signal to noise ratio. It can read clean and it can read low. The specification is a ½ foot per second. So again, we can read way down there and again, very clean water. Here's an application where you can see the laser beam hitting the water. In this case, that water, you can see the surface looks like glass. It's barely moving. Very, very challenging. A non-laser application or a non-laser technology would not work so well here because you need some surface velocity for a radar unit to work. The laser is able to read that. Okay, we often get asked, how do we install these things? We only need a small opening, roughly 4 inch by 15 inch wide or something like that would be just fine. This is the ISCO Flow Lab. So you can see very easy to do that. Here's what the laser looks like when it hits the water. So we got a nice tight point, nice laser focus. Here's one that's an industrial application. And this is ideal. If you can design this way, you're going to be right on the nose. And the laser is spec'd at 4% accuracy. So you should be right there when you look at something like this. Here, just a small opening in the top of that pipe. We have a nice contained area. There's no pipe joints, no inverts. It will get really, really good accuracy in this site. Here's one that was a wastewater effluent discharge line. very challenging, a lot of entrained air bubbles, turbulence, foam, you name it. So we went ahead and they installed a laser, and this is what the data looked like. So we had level, velocity, and the flow rate. The velocity, what I noticed with this was we were seeing a lot of drops, but they weren't going to zero. They were just going way low. After further investigation, looking at some of the diagnostics of the laser, we were able to see we were getting a low frequency, low velocity return, but we were also getting what we really wanted, which was the higher velocity. What I was able to do was go ahead and tweak this and adjust so that we only look for something above, in this case, that 1 meg line there on the bottom. So now we're able to filter out what it sees and what we know is real. This solid red line is the time when I made that change. So from the right on, once we made that change, it looked really, really good. This was going to cost them a lot of money to go ahead and redo that whole effluent line. So again, minor tweaks were able to get the laser to do what they needed to do. Okay, if I have a line that maybe it's not exactly perfect and it's dumping out, we can do a remote ultrasonic sensor, and that will mount up normally into the pipe, mounts at a horizontal bracket. We know where the water is, we know where to focus. We are able to get even a more accurate measurement during those conditions. Okay, so we have applications too where people are looking at river. Why is that challenging? Well, we all know we go from low flow to raging rapids during storm events. You put anything in there, first of all, putting any cables or sensors is not a good idea. Vandalism purpose, people are going to do that, as well as just debris catching on those. And you're going to have some inaccuracies due to the technology. With a large area like that, it's difficult to measure it. So you're going to have some problems. The laser, the good thing about that is it can read very slow and low flow. So we can read down to almost a crawl. It can adapt to the high flows as well. So it's going to do a good job overall on that application. And there's nothing in the water, so you don't have to worry about something getting torn out. Here's a good example of one that was a site in Lincoln. And you can see normally when they had flow, they had no flow, or they had a lot of flow here. So this was a really, really good way of measuring that as opposed to putting something in the flow. Okay, so what happens? We're going to wrap up here in a few minutes, but I wanted to talk about what do we do when it goes underwater. This is one that was in Michigan, and the thing gets covered quite often. Anything covering it like that is going to make it difficult to measure, so you may have to clean it off. But the laser is designed for 6 feet submergence, 72 hours. In this case, they went ahead, they had a nice log chain attached to it, so it will not get torn out of there. So what happens with this unit when it goes underwater? There is a sensor on the bottom, a continuous wave, like Steve talked about earlier, that is going to measure the velocity using a Doppler sensor. But it will use a pressure sensor to measure the water depth. So it will know very accurately all the way through the range of the submergence, just how far underwater did we go? How surcharged did we get? So good way of doing it. Nothing is perfect in these types of applications, but this is about as good as it goes. The air pocket design is again there so that we protect or keep water off of the laser optics. All right, so we're going to go ahead and wrap up. In conclusion, open channel flow is challenging. Nobody said it was easy. I think in the old days it was, or people thought it was, because all you had to do was do a simple level measurement. What we're finding out is that flumes are not always accurate because of the application more than the actual flume. The flume is a good design, but maybe your application isn't quite as good as you thought. The installation is not perfect. But if you do have a good installation, you can get accurate data, and normally in the 5% range. Area velocity, that's becoming the way of the industry, and we see it all the time, a lot of times more for I&I studies, but we are also now seeing it more for billing applications, as Steve mentioned earlier, and things like that where you don't have to put something in the water itself. So, but the diagnostics really help us and you determine, is this thing working right or is it not? Remote communications. So this is another big one. Everybody is going to cellular. You will be seeing Flowlink Cipher out shortly. That is our web hosted version of software that will allow you to transmit data from the field to the web and be able to view all that remotely. So again, a lot of good stuff out there, but bottom line, you need to know how to interpret your data to be able to determine, is it valid? Is it usable? And where are we at with that? And we can certainly help you. We have a thing called the 2100 series white paper that is really good to explain diagnostics and what they do. And that's online. You can download that. Feel free to give Steve or I a call or an email at any time. rick.dye@teledyne.com, steven.mcmanus@teledyne.com. So feel free again to get a hold of us anytime you want, and or any of the other application staff. So we have a good group of guys there that can help you out. And with that, I'm going to open it up for questions.